Okay, so welcome back for the afternoon session. And our first speaker is from my institute, ISI, is a PhD student, Sumit Kumar. And he will talk on spectral aspects of convexity for L functions.
Thank you, Saurabh, for the introduction, and a big thank to the organizers for the opportunity. So today I'm going to talk about spectral aspects of convexity for L functions. So here is the overview. Here is the overview of my talk. So I will say briefly about L functions and the L function which we encounter in number theory are automorphic L functions. And then I will define what is subconvexity. And then I will say briefly why subconvexity is important. And then the existing state of art, the methods and existing results, followed by my main results. And if time permits, I will give brief ideas about the proof. So let's get started. So the story began in around 1920 with the Riemann-Zeta function, and you have seen it many times today and tomorrow, yesterday as well. So it's a nice series which is convergent for real part of S bigger than 1. And Hardy and Littlewood proved that the zeta value on the critical line, half plus it, is bounded by modulus of S to the power 1/4 minus 1/12. So you might wonder here that why does it make sense, first of all, to talk about the zeta value, zeta at half, because a priori it is not convergent here. And how does one gets the exponent 1/4? And why do we really care in getting the exponent 1/4 minus something? And here I'm taking it to be 1/12. So we will try to answer this question in coming slides. So, and let me just remind you the symbol. So less epsilon symbol here means the left hand side is bounded by some constant which will depend upon epsilon times the right hand side. And I will use it time and again. Zeta function is a part of a big family, and the family of automorphic L functions. In fact, it is a degree 1 automorphic function. And what is an automorphic L function? So it's a Dirichlet series of so an automorphic L function of degree D, which you associate to an automorphic form. So it is a Dirichlet series lambda fn by n to the power s, which has a degree D Euler product. So here in the product, alpha jp's are known as local parameters at the prime p, and lambda fn's are the Fourier coefficients of the form f. And it is convergent for real part of S bigger than 1. Moreover, it is known that it has a meromorphic continuation to the whole of C, complex plane. Moreover, it satisfies a nice functional equation. Apart from having meromorphic continuation, it has a nice functional equation which says that you can relate the value S to the value 1 minus S. So here we have some factors. So this lambda SF is called a completed L function. So you just complete it by multiplying this L infinity SF times this QF to the power S by 2. So this L infinity SF is called the local factor at the infinite place, which is defined by the product of D many gamma factors. So note that this muses, which I have colored in blue, they are called local parameters of F at infinity, and I'll be focusing more in the later part of my talk. So always keep these muses in mind. And the integer kf, which is a natural number, is known as the arithmetic conductor of F. And there is another factor, epsilon F, which is known as the root number, which has usually modulus 1, and F bar is the dual form associated to the form F. So let's try to give some example to understand these L functions. So in the case of degree 1, the Riemann-Zeta function, classic Riemann-Zeta function, is one such example. And in this case, you take F to be a trivial form, trivial representation. So here their spectral parameter won't come up. They are just 0. This alpha j p's are all 1, and also arithmetic conductor is 1, and there is no root number. So it's a even much more simpler functional equation here. And another example is the Dirichlet L function. So let's take even Dirichlet character modulo a prime d, and you define this L function simply by taking the coefficients chi n by n to the power s, and it has a degree 1 Euler product, converging again real part of s bigger than 1. And in this case, functional equation, if you observe functional equations, so just focus on these two factors. So this blue color d. So in this case, arithmetic conductor will be d, and the epsilon f, which is a root number, it will be the Gauss sum associated to chi divided by square root of d, which is again of modulus 1. And chi bar is the usual inverse of chi. In the case of degree 2, let's move on to degree 2. And we have already seen the forms. Take F to be a holomorphic Hecke-Cusp form for SL2Z having weight kf, and let lambda fn be the normalized Fourier coefficients. So normalized means lambda f1 is 1. And you again associate an L function corresponding to f. So in this case, observe it is of degree 2, and this alpha fp and beta fp are related by these equations. So their product is 1, and their sum is the eigenvalue, these coefficients at the prime p. And the functional equation, so when you write down the functional equation, in this case, these local parameters will be now involving these weights, kf minus 1 by 2 or kf plus 1 by 2. And the root number is also nice, I to the power kf. And a similar thing you can define for mass forms if you are aware of them. Let's move on to degree 3, a bit more complicated, higher degree L function. So take pi to be a mass cusp form for SL3G having Lagrange parameters, or if you say, you can say local parameters. They will be of the shape mu1, mu2, mu3. There is a typo, so mu3. And for a coefficient, let's say they are lambda pi n, comma r, all normalized, and you define. So just observation is that there's some mu1, mu2, mu3 will be again 0, and the Ramanujan conjecture predicts that is mu pi, this whole mu pi will be all, the mu's will be all imaginary. So they belong to IR to the power cube. And again, we associate an L function involving the coefficients. So this time the coefficient will come up is lambda pi n, comma 1. And it will have an Euler product of degree d. And now if you see the functional equation in this case, so these mu's will again come up, and they will satisfy this. The sum is 0, and you can for simplicity take mu's to be imaginary if you wish. And pi bar is a associated dual form. Let's move on to even higher degree. So degree 6 L functions. So don't worry about them if you have not seen them, but just think of them as product of GL3 and GL2. So take a GL3 form, which I have defined in a previous slide, and the GL2 form, take a modular form. And now you associate using these coefficients, lambda pi n1r, lambda fn, over n r squared to the power s. So it is known to be a degree 6 L function. It is automorphic, and in fact, you can show that it is shown that LSF times chi is just same as LSF, and where f is some GL6 automorphic form. And it has again nice functional equation with root number I to the power kf, and qf arithmetic conductor will be 1, and the gamma factor. So also just here focus on these gamma factors, which will be 6 many, and they will be involving gamma factors, these local parameters involving the GL3 forms and GL2 forms. So muses are the local factors, local parameters coming from GL3 forms, and kf minus 1 by 2 or kf plus 1 by 2, they are associated to the GL2 form. So you just add them up, and you, in this way, you will get 6 many gamma factors. So what does functional equation do? So usually, so what we want to do actually with this L function now, so we really are interested in understanding the size of this L function, LSF, and we want to understand how large or how small it is. So if you apply functional equation simply, then the problem boils down to understand it inside the critical strip, real part of S between 0 and 1. Moreover, it just boils down to estimate it on the critical line. You apply complex analysis, Fragment, Lindelof, and everything. So you can just restrict yourself, and you can focus only on the central line half. So here is the summary. So what does the functional equation do? So if you have point S to the left of the half plane, and then you can relate by the functional equation to the point 1 minus S. So things are nice in this region, right half plane and the left half plane. And in between, in this critical strip, it is all mystery. It is all mystery. And we are really interested on this line half. So this picture, I have taken it from Malisham, from his slides. So let's move on. So to estimate this L function, we really need to define something, a parameter called analytic conductor. So for this purpose only, and Ivany-Charnak introduce a function which we call analytic conductor, which will involve this parameter T, R plus IT, this T1, arithmetic conductor, and μf, spectral parameters or local parameters. So it is defined as simply the arithmetic conductor times this function T minus muses, and then D many times. You just vary them. And so if you just there is a conjecture known as the Lindelof hypothesis, generalized Lindelof hypothesis, which predicts that these L values on the central line are bounded by analytic conductor to the power epsilon, and epsilon can be taken as small as you wish. And this also follows from generalized Riemann hypothesis, which you have seen it many times. So, but that's very far from our reach and with the current technology. So what do we know? So if you just apply functional equation and Fragment-Lindelof convexity principle, you can easily get 1/4. So the L half values are bounded by conductor to the power 1/4 plus epsilon. This is known as convexity bound. So what is subconvexity? Subconvexity problem is to get a bound of the form 1/4 minus delta. So delta can be as small as you wish. But the important point is you have to reduce the exponent 1/4. So you can reduce it by 1 by 1 lakh. It doesn't matter. And usually in applications, we really are interested in estimating these bounds with respect to a single parameter. So in these problems, basically the main 3 parameters are T, arithmetic conductor, and these local parameters. So if you just vary this conductor, arithmetic conductor, and get a subconvexity, we call it level aspect subconvexity. If you vary this parameter T, so half plus IT, T is large, going to infinity, say, then if you get subconvexity in that aspect, we call it T aspect. And if you are interested in varying the spectral parameters, which are basically known as the parameters, real parameters of the form F. So in this case, subconvexity will be known as the spectral aspect subconvexity, and we will be focusing more on this in later part of my talk. So here, the norm of μf is the product d many factors 1 plus μi's. So if, for example, if you take μi's to be of size t, then this will just look like t to the power d. And yeah, that's all I have said. So why do we care? So there are some fantastic applications of subconvexity. So in 1937, Ingham showed that if you know the bound of the form, so the zeta value at half plus it, if this is bounded by 1 plus t to the power c plus epsilon, then you can show that the gaps between consecutive primes is bounded by pn to the power some theta, where theta is some function which looks like 1 plus 4c divided by 2 plus 4c. For example, if you plug in the value c is equal to 0 here, you can show that pn plus 1 minus pn is bounded by pn to the power 1 half. But this c is equal to 0 corresponds to the Lindelof bound, which is very far. But so if you apply various subconvexity bound, you can get a better approximation of p to the power theta. And so this theta n will be smaller, coming towards half. And there is another interesting application of subconvexity for zeta function again. So the subconvexity for zeta function is related to number of simple zeros. So this n naught t denotes the number of simple zeros of the zeta function in the rectangle with height t. So Conray, Ghosh, and Gonek shows here that if you know this bound, then you can show that this number of zeros, simple zeros of the zeta function in this rectangle of height t are like t to the power theta 1c. So again, theta 1c, we really wish to take it to be like 1. So indeed, if you take c to be 0, which correspond to the Lindelof bound, then you can show that this according to this result, then you can show that the zeta this n naught t is bounded below by t to the power 1 minus epsilon. And note that we expect all the zeros to be simple. So still, this result won't give you the exact size, but it is very approximate. It's very near still. So another application in equidistribution. So if you prove, so there is the result of Duke, Friedlander, and Ivanich, who show that if you prove level aspect subconvexity for GL2 forms, holomorphic forms, then you can get equidistribution of certain lattice point on the unit sphere. So again, if you look at this picture, so the big sphere is centered at 0 with radius square root n. So you are interested in counting points on the unit sphere. So how do you get this point, lattice point? So you just project this XYZ, which is on the big sphere, project it down on the unit sphere by dividing by root n. So now these will be points on the unit sphere. So the subconvexity implies that these points, these kind of lattice points are equidistributed on the unit sphere as long as n is not congruent to 0, 4, 7. So there are still a lot of points, and you show that they are equidistributed. It's a really good application. And another application is quantum unique ergodicity, which you have seen in many talks, but I have not mentioned that. So that is related to the subconvexity of sim square in the level and spectral aspect. So what are the existing methods and the results? So let's see. So there are classic results. So the first such result is this while bound, which I have mentioned in the first slide by Hardy-Littlewood and Landau. And if you, so here the bound is now 1/4 minus 1/12. So 1/4 is again convexity, as you have seen, and you are reducing it by the exponent 1/12. So Hardy-Littlewood and Landau uses while shifting technique. So they just what do they do is they want to get cancellation in summation n is of size, let's say capital N, and n to the power it exponent. So by showing cancellation using the while shifting, they prove this bound. And then Burgess bound, which came a bit later in 1962, and he shows that the zeta value, L value at at half of this associated to this Dirichlet character, they are bounded by p to the 1/4 minus 116. So again, a subconvexity, p to the power 1/4 is the convexity, and chi is here a character modulo p. So the Burgess method, you can think maybe as a variant of while shifting, but in arithmetic conductor, in arithmetic context, but it has many significant differences still. So these are the classical results, and it's very difficult to adapt them in higher degrees, say for degree 2 and degree 3 onwards. So for degree 2, the first result was by Anton Good, who used spectral theory of Laplacian in 1982, and he basically computed the second moment, the second full moment t to 2t of this L value, and got the t aspect subconvex bound, which is of same strength as Weil exponent, which we have seen for zeta function. And then this amplified moment method, which is one of the existing and important method, which is still being used to solve many problems in subconvexity. So which was introduced by Iwaniec, and the first such instance was to get spectral aspects of convexity for holomorphic or mass forms. And then there are further development by Duke, Friedlander, and Iwaniec, and they solved level aspects of convexity for GL2 forms. There are further refinement of amplified moment method by Conray, Iwaniec, and Petro-Young. Very recent result in which Petro-Young they show wild type bound for again in the level aspect for GL2 forms, and Conray, Iwaniec they kind of use non-negativity, and because they are looking at the third moment. So here, if you see in the first slide, it's also kind of a movement, but it's a second movement. And in other results of DFI, they are sticking to second movement, but Conray, Iwaniec, they did it for the third movement, but they have to use non-negativity. So then further, in the case of Rankin-Selberg L-functions, again, adaptation of the moment method, amplified moment method, it was done by Michel, Kowalski, Vanderkam, Harkos, Blumer, Sarnak, and they obtain subconvexity for various Rankin-Selberg L-functions. So if you know, they are basically degree 4 L-functions, and they are obtained by degree 2 L-functions. So multiply, you just take convolution of 2 GL2 forms. So they showed level aspects of convexity and spectral aspects of convexity, but here only in the few cases, so only the level of one form or spectral parameters are of only one forms varies, not both. That is a much difficult problem. And then there is a more sophisticated approach by Michel, Venkatesh, Bernstein, Reznikov, Sarnak, and others. So, and using this approach, Michel and Venkatesh showed subconvexity for any GL2 L functions in all aspects uniformly. And Bernstein, Reznikov also used similar approach to give subconvexity for some degree 8 L function. So for degree 3, if you go to higher degree 3 L function, the problem was open for a longer time, and in the last decade, in 2011, the first result for such GL3 forms was obtained by Xiaoqing Li. So she considered self-dual GL3 forms. So self-dual GL3 form means their dual is same as them, and you can consider symmetric square function, so they are self-dual. So she showed that this L values is bounded by t to the power 3/4 minus 116. So note that here T to the power 3 by 4 is the convexity. So conductor, analytic conductor in the T aspect should be T to the power 3 because the degree is 3, and then the convexity will be T to the power 3 by 4. And she obtained the bound 3 by 4 minus 116. So, but she has to assume self-duality because she adapts Conray-Vannier approach. So due to this, she has to assume non-negativity. And this bound was further improved by many authors. This bound was further by many authors, and the latest bound is by Lin, Nunes, and G. So Lin will be talking about this in his talk. So for more details, please follow Lin's talk. And then a big breakthrough in the spectral aspect was by Blumer-Butkin, where he obtained subconvexity for GL3 forms in the spectral aspect. So T pi, so here T pi is are the size of these parameters, mu i's, and they take these parameters, local parameters, to be in generic position. So by which we mean that all of them having size T, and their difference is also size T. And they prove subconvexity. Their exponent is very bad, although, but still they manage to get subconvexity. But what do they use? So they use amplified moment method again, amplification technique, along with so they estimated the fourth moment of these L values, and they averaged over the GL3 forms. And so this result was recently improved by Prahlad Sharma, who is in the audience, and he got still a better bound, and he generalized the same method, and indeed he considered the form GL3 times GL2 form, Rankin-Selberg form GL3 times GL2, and obtain a much better bound. And if you take the GL2 form to be Einstein series, then you can recover this bound, recover this result, and with better exponent. So let's move on to any higher degree. So what's known for higher degree? So a very recent result of Paul Nansen. So he resolves subconvexity for any degree DL functions in the T aspect and the spectral aspect. So in the spectral aspect, he assumes that these parameters, local parameters, are having uniform parameter growth. So by uniform parameter growth, he means that these muses are all having size T. So each of these musae, so there are D many, so mu1, mu2, mu3 up to mu D, all have to have same size. And he showed subconvexity in the T aspect and in the spectral aspect. Although his bound is not very strong, very weak, but still he gets subconvexity. So what does he use? So his method is inspired by amplified moment method again, you can say that. And but there are other tools from representation theory. And so what lies ahead? So in the level aspect, subconvexity is still open. In particular, and one interesting case is the symmetric square L function, which is self-dual degree 3 L function. So in the level aspect and in the spectral aspect, the subconvexity is still open. And it is indeed a difficult problem. It is related to the quantum unique ergodicity conjecture, in fact. So very recent method of delta method. It was introduced by Munshi around 10 years ago. And he developed it in a series of papers. And with this method, he resolved subconvexity for any GL3 forms in the T aspect and the level aspect. So level in particular twist by a character. So note that here he doesn't need to assume this GL3 forms to be self-dual, And in this way, he generalizes the result of Cauchy-Lee. And the first instance was level aspect subconvexity in the level aspect for GL3 forms. And using the similar techniques, he applies them to GL3 times GL2 L-functions. And in 2018, he gets a T aspect subconvexity for these particular degree 6 L-functions. So since then, many people are working on it, trying to understand this. And there are some different variants of delta method approach by Keshav Agrawal, who is in the audience again, and Roman Holonsky, Lin, Lensons, and many others. So there are different expression of delta method that you want to explore, that which one to use. There are many such expression of delta method. So a very recent result of Pilar Sharma, and he applied the delta method, and he obtained subconvexity for GL3 times GL12 function in the level aspect. So this result again generalizes Munshi's result in the level aspect. So let's move on to our main results. So we want to study the delta method in the spectral aspect. So we are considering GL3 times GL12 functions, and we want to apply delta method to get subconvexity in the spectral aspect. So here GL3 also has spectral parameter and GL2 also has spectral parameter. So either these GL2 parameters can vary or GL3 parameters can vary. So we will try to see them. So let's recall again. So take pi to be a mass cusp form for SL3Z having spectral parameters μ(z), and take F to be a holomorphic cusp form with weight Kf. You can, if you wish, you can take also the mass form having parameters Tf. And you again consider this L function associated to the form pi and F. So, and recall that the local parameters in this situation are μ(z) plus Kf minus 1/2 and μ(z) plus Kf plus 1/2. So there are 6 many local parameters. So there are two instances, there are two situations. So the first situation is when you fix Kf. So they are like constant, you can forget that. So then in this case, the GL3 forms only varies. And that is called the GL3 spectral aspect subconvexity. We call it GL3 spectral aspect subconvexity. And if you fix GL3 form and vary only GL2 forms, then we call it GL2 spectral aspect subconvexity. So the first result is in the GL2 spectral aspect. So if you fix the form GL3 form and vary the form F, which means that these weights are going to infinity, then we get subconvexity for these L values. So here in this case, this Kf to the power 6 will be the analytic conductor, and then you get the bound 1/4 minus some 1/306. And so this result actually generalizes Cauchy-Lee's result to all GL3 forms. So she proved this result for only self-dual GL3 forms. And now let's move on to GL3 spectral aspect. So this is kind of more interesting. So here we are taking F to be fixed, and the GL3 form varies. And let's take this μ(z) in non-generic position. So in by non-generic position, I mean, so you take all these μ(z) of size capital T and their differences. So μ1 minus μ2 and μ1 minus μ3 is of size T, but μ2 and μ3 are nearer. So by which I mean that the difference is like T to the power 2/3. So, and the rest are having at the generic distance. And then we prove subconvexity in this situation. So again, in this case, note that the analytic conductor is T to the power 6, and we get subconvexity. So earlier there was a result for GL3 spectral aspect by Blumer-Butkin, but he considered the generic range. So in his result, he considered these parameters are having size T, and all the differences are also having size T. But here, note that we are taking the difference to be smaller. And like ultimate goal should be that can you prove subconvexity when they are just same, say mu2 is equal to mu3. So that is even a difficult problem. So let's move on to our next result. So indeed, we also consider the spectral parameters to be in the generic position also. So again, like in Blumer-Butkin result, and we also get subconvexity here. So T to the power 6 to the power 1/4 minus 1 by 96. But we have to assume a condition on the Fourier coefficients of GL3 forms. So here we need to assume that this summation L is of size capital T. L we are taking to be prime. So we want to we really should have that these coefficients, L2 coefficients should be like L to the power 1 minus epsilon. So here L is like T to the power 1/4 for us. And in this way, in this result, we generalize Blumer-Butkin result, modulo this assumption. So we will talk about this assumption later a bit more. So now let's move on to the third result, which is even more interesting, and we call it the conductor dropping case. So in this one, we consider these parameters. So we are taking mu1 and mu3 to be of size capital T, and the mu2, let's take mu2 to be of size T to the power 3/4. So it's not of size T, but it is much smaller than size T. So we are taking it to be, let's say, like T to the power 3/4. And then the difference will be of size capital T only. So in this case, note that the analytic conductor will be smaller. So in this case, analytic conductor will be T to the power 11/2, which is smaller than T cube. So the conductor is dropping here, and we get subconvexity for this kind of forms. And again, we have to assume this L2 norm condition, lower bound condition on this GL3 Fourier coefficients. So I mentioned Nielsen's result, Paul Nielsen's result in spectral aspect. So he doesn't cover this case. So he has to assume that all these parameters, mu1, mu2, mu3, have to have the size T. So he cannot drop one of the mu's to be, say, T to the power 3/4. So note that this can be thought of. So let me say more about this third result. So the above result, this conductor dropping case, may be thought of as a one step closer to the subconvexity for Sim square in the spectral aspect. So in the case of Sim square, what happens is, so this one of the parameter mu2 will be exactly equal to 0, and this mu1, mu3 will be of size T, and mu2 will be exactly equal to 0. So we will not have any size. So in this case, in the case of Sim square, the conductor will be just T square, much smaller than what we have here. So that's what I'm saying here. The Sim square has parameter like, they will have like T0 minus T. And we are taking the parameters like T minus T to the power 3/4 and T to the power 3/4 and minus T. So there is a recent result of Khan and Young. So where they obtain subconvexity for Sim square F in the hybrid. So T, they vary T aspect and spectral aspect. So they are kind of varying T and as well as the spectral parameters. So in their case, analytic conductor is kind of T to the power 20/7. So you can compare by taking F2B and Einstein series. Our result can be compared with their result. So in our case, so note that in our case, our analytic conductor is T to the power 11/4, and theirs is T to the power 20/7. So which is smaller than, which is larger than ours. So let's talk a bit more about the assumption. So we have to assume that these L2 Fourier coefficients are large. And so this usually will comes up when you apply the mass transfer trick or amplification trick. So it's a repercussion of that. So it appeared also in many papers of so Ivanich in the spectral aspect paper. This similar condition was also present, but there these coefficients were GL2 coefficients, and a result of Rizwanul Khan, where he showed subconvexity level aspect subconvexity for GL3 times GL2 in the GL2 level aspect. So he also has to assume such kind of condition. So we only know that this parameter, this L2 norm, is bounded by L to the power 1/3. So, but even if we can show that these are bounded below by, let's say, L to the power 1/2, then also it will be suffices for our purpose. But that we don't know that. So, anyways, this condition, this assumption, we expect it to hold for all the forms, for all GL3 forms. So it's not any mysterious thing. So let's in coming 10 minutes, I will now talk about some ideas about the proof. So the ingredients, main ingredients are, the first step is just to apply the DFI delta method. The DFI means the Duke Friedlander Ivanich delta method. Then we apply the conductor lowering trick, which was also introduced by Munshi in his many papers. And then we need to apply mass transfer trick in some of our result. That's kind of necessary. And there is a new input in this paper, which we call spectral killing trick. So we introduce a factor which will help us kind of saving more when we apply various summation formula. So it's an important trick which we have to play to get our result. And then we apply various summation formula. So let's give a brief sketch of the proof. So let's take these forms to be in non-generic position. So that was our one result. So take mu as to be of size t, and let's take mu2 and mu3 of size t to the power 2/3. Smaller, their difference is smaller. And so if you apply functional equation, so the problem boils down to getting cancellations in these exponential sums. So here you have a sum of, so n is of size capital N, which means that n is small n is in between n and 2n in the dyadic range. And these GL2 coefficients and GL3 coefficient and GL2 coefficients. So we really want to get cancellation in this. So if you just trivially treat it, apply the Ramanujan bound on average, then you can show that this is bounded by capital N. So to get cancellation means we really want to get a bound of the form n to the power 1 minus delta or any delta. So that will solve our problem. So how do we do that? So the first thing in the delta method is to separate the oscillations. So the first thing that is the kind of theme of the delta method is it works very well when you really want to separate these oscillations, and then you play around with the separated oscillations separately using Voronoi summation formulas and all. So we do that. So we are separating it by this delta symbol. So this delta of n minus m. So we are simply writing this expression into this this double summation, and this delta of m minus n is the Kronecker delta symbol, which is defined to be just 1 if n is equal to m and it is 0 otherwise. And now we apply some non-Fourier expansion of this delta symbol. So we use this DFI delta method, which is expressed kind of, which is kind of a Fourier series expansion. And so if you see it here, so there are some additive characters floating around. So E of A n minus m by q. So you are summing over this variable A, and you are taking a sum over this variable small q. And in this method, the size q is usually square root of n. So n is here the size of the equation n minus m. So n and m having size n, so is the equation n minus m. So in the delta method, the size of the equation, so the q usually has to go to up to size n. So usually we can do one thing and then simply just keep on applying this delta method and separate the oscillations. So if you just plug in the expression, and now this n variable and m variables will be separated. So the next obvious thing now from here onwards will be to apply various summation formula. And if you see what you gain in the summation formula is that it is really helpful if your capital Q is smaller. So suppose you can choose somehow Q to be, let's say, root n by something. So it is really helpful to when you apply the summation formulas. So we do that. That's the theme of conductor lowering trick. So we do that by introducing a V integral, which is of size capital K, less than capital T. And when you apply this integral, it will reduce the size of Q to square root of n by K, and which is really beneficial, and it's a kind of must here. And so once you apply that, then your expression will look like this integral and these summations. So this n minus m by n to the power minus iv is the reason for lowering this size of Q is this factor n by m to the power iv. And so we also have to introduce this factor n by m to the power minus I imaginary part of mu3. So this we are calling it the spectral killing factor. So at the moment it's not clear that how it is helpful, but because this is an artificial factor. But when you just plug this in and apply summation formula, GL3 Verona summation formula, so this will kill one of the parameter and eventually helps in saving more in the dual length. So when you plug this in, you will get an expression like this. And now you apply the DFI delta method. So apply DFI, and then you apply various summation formulas. So GL3 Verona summation formula and GL2 Verona summation formula. So for example, the GL3 Verona formula will give you the dual length to be like, so the dual length will be like Q cube K square T by N, and this GL3 coefficient, and here this S A bar NQ is the Clusterman sum that will come up, and there will be some integral transforms. So note that this factor, now notice the importance of this Q. So Q is coming in the denominator. So if we don't apply conductor lowering, that the size will be bigger, and you eventually save lesser in this situation. Sorry. And similarly, when you apply this spectral killing trick, so this K square factor also comes up. So if you don't introduce that spectral killing trick, in the numerator you will get Q cube T square K, which is smaller than, which is bigger than what you have here. So now you apply Verona summation formulas GL3 and GL2. So now here is a crucial observation that was also presented in Munshi's paper. So what does it do is that the sum over K, the character sum, will, so if you evaluate the sum over A, so this S A bar N is the Clusterman sum, and E of A bar M by Q will come up when you apply the GL2 Verona formula. So if you evaluate this, you will get an additive character in the variable N, so which is very important when you want to apply various other summation formulas later on. So now after applying the Verona formulas, you apply Cauchy. so that you break the involution. So if you again, because if you don't apply Cauchy and apply summation formula, it won't help at all. So you have to break the involution somehow. And then you apply Poisson summation in the n variable again. And you save root q extra. And that you save because of the additive character you have that I showed you in the slide. So because of this additive character, you are saving root q extra while applying the Poisson summation formula. And then then you apply, then you treat the zero frequency and non-zero frequency case separately, that you have to do. So zero frequency, by zero frequency, I mean you have to treat the case n is equal to 0 separately, because there won't be any oscillations there, and you have to treat it trivially. In the non-zero frequency, there will be oscillations, and you will save root q extra, as I mentioned. So in the other cases, so I'm just mentioning these steps for the spectral parameter when they are in non-generic position. So in the other two theorems, you have to apply the mass transfer because you won't save enough in the zero frequency, and you will save sufficient in the non-zero frequency. So to balance this up, you can transfer some mass. That's what we do in the other theorems. Thank you for your attention.
Okay, thanks for the nice talk. Now, is there any question? Yeah, Ratnadeep.
Which one? Okay. This one? So delta, so this delta will reflect in the subconvexity. So delta is very small. You can kind of take it to be like epsilon. So it's very small for us. So this is for the purpose of getting subconvexity. So this you focus on this 3/4 here. So whatever margin you have in the size, that will reflect in the subconvexity. Sorry, maybe I'm not sure, but it will depend upon that. So, yeah.
Any other question?
So regarding this lambda pi 1L squared, this lower bound, so your lambda pi 1L is a Hecke eigenvalue, right?
Right.
So suppose I take self-dual and then do Rankin-Selberg. I mean, this will be smaller than the Rankin-Selberg sum, but you can't get anything from that?
No, because they are more general sum, first of all. And
yeah, they are like nm squared. So you're fixing n as m and l. So as I'm saying, it will be smaller, but you can't manipulate the other terms, is it?
So other term means, I think what you're talking about is, so usually what we know is that either lambda pi 1L or lambda pi 1L square, lambda pi 1L cube, one of them is big. That's what only we know. So if you can somehow manage the other two terms, that also will be fantastic, but we cannot do that.
You don't get anything for the lower bound, is it?
We know only L to the power 1/3.
How much?
1/3.
Oh, 1/3, but I see.
But we need.
But you need much larger.
Even if we could get L to the power 1/2, that will be suffices.
That will suffice?
Yeah, even 1/2 is also good for us.
I see.
Yes, even 1/2 will also be good for us.
Okay, I see. Okay. Thank you. Yeah.
Any other question? Any question in the chat? Okay. I have a question. So when you apply the spectral killing trick, what happened to the m variable?
M variable doesn't change. So
m by n to the power I.
So yeah, m some power of m will be there. Let's see. Just a minute. here, right? So yeah, so here is also a factor like m to the power minus imaginary part of mu 3 times v. So yeah, so here it seems that you might lose a little bit, but that you can save later when you apply the Poisson summation. So you might lose a little bit here, but right. So in that case, your m length will be a big larger dual m length, but that might help you in that will help you in saving when you apply the Poisson. So that's fine.
So if there is no more question, let's thank the speaker again. And so the next talk is at 4, right? Yeah. So we will resume. Okay, one more question.
Sorry? Here, we can take F2B as instances, right? So yeah, even pi can be taken as instances. So if pi is fixed in the first result, so you can also get, in this way, you can get subconvexity in the GL2, GL3, GL3 times GL2 in all L functions. One of them should be cusp form. Yeah, cusp form we can. So if you are taking instances, there will be a main term, but that can be managed.
Okay, so we'll resume at 4 for Matt Young's talk. Okay, thank you.